So at this point we've learned about Hubble's law, and we know the universe is expanding, and that expansion is telling us something about the history of the universe. Ever since expansion has been discovered, astronomers have wondered how that expansion rate has changed over time, or whether it's changed over time. And it's illustrated with a relatively simple graph. Consider this graph with me. On the vertical axis, we can put the size of the universe. Okay, and you can measure that however you want. Maybe you want to say it in miles or in billions of light years. Okay, but we aren't going to specify that. We're just going to have a general representation of the size of the universe. And on the bottom here, we're going to have time. So right here we have today. Okay, so I'll put today. So today, the universe is of some known size, right? Our observable universe has a size of roughly 14 billion light years. So we'll put a dot right there. Now we also know that at some point in the past, right, at the beginning of the universe, it had pretty much no size. Began at just a point. The question is, what is the shape of this graph over time? Right, now we have 2 points. So I want to draw for you a couple possible shapes, and those shapes really tell us a lot about the universe. Alright, so it could be that the universe started expanding right after the Big Bang, and it's continued expanding at a fairly constant rate, and that it will continue this constant expansion forever. Right, it just keeps on going. That would kind of make sense. You'd think, right, there's an explosion, just keeps expanding, goes out, it's just kind of coasting out through space. It would also perhaps make sense that, well, this universe, right, it's full of huge galaxies, which have a tremendous amount of gravity, right? And so all those galaxies are pulling on one another, and presumably that mutual gravity of all them pulling on one another would sort of slow the expansion down, right? That kind of makes sense. So another possible shape of this is that maybe that expansion of the universe initially was actually, let me choose a different color. Maybe the expansion of the universe started out faster than it currently is, right? But as all that gravity from all the galaxies started pulling, it has kind of slowed the expansion rate down, right, until we see its current state. And then you might ask, well, what's going to happen? You know, we might continue to expand for a little while, but if it's really slowing down and that gravity's pulling, perhaps the gravity is going to pull so much that it actually reverses the expansion of the universe, right? And that the size of the universe starts to decrease, and all these galaxies come back together, eventually into some sort of big crunch, as it's sometimes called. So this is another possibility, right? We know the universe is expanding, we know roughly at the rate it's currently expanding, but we don't really know how well, at least we didn't until recently, we didn't know how much this expansion rate has changed. So this was sort of a commonly held possibility of a big crunch that may happen. What's fascinating, especially in light of some of our conversations about the Big Bang, is that this appealed to those astronomers who really wanted a steady-state universe, who really didn't like the idea of a beginning to the universe, and so this offered the possibility of what they might call an oscillating universe, that there's a big crunch which is in fact a new Big Bang, right? And that you could have another expansion, and that you might have universe after universe after universe that keeps resetting itself. Very interesting. Another possibility that was suggested, let me get another color, was that the universe is pretty much expanding at a more or less constant rate, and that it will continue to slow ever so slightly, but that even though it's slowing in its expansion, it will continue to expand forever. Right? So it'll never turn around. There's not enough mass in the universe to turn it around. Okay, so to specify these different possibilities, right? This is telling us something about how our universe is expanding, and it's telling us something about the future of our universe, right? And how it will eventually end up. Will it turn around and have a big crunch? Will it just slow down? Well, this can be specified with 2 different parameters. They're often called the cosmological parameters. Okay, the first cosmological parameter is one that we've already seen before, and that is Hubble's constant, this H0. Hubble's constant is a measure of the current expansion rate of the universe. So if you will, it's kind of like it's the slope of this line, right, at today's value, at today's point. This tells us, sort of indirectly, we take the inverse of it, but it gives us the age of the universe, right? So it's sort of like an average expansion rate. Maybe I'll put that instead. It's an average expansion rate. Okay, the next cosmological parameter that we want to look at is this omega m. And this is essentially a measure of how much mass is in the universe. So if you took every galaxy and added it all together, you'd say how much mass is there in the whole universe, right? And that's a measure of this omega m. Now you'd get a sense that this would be relevant to how the expansion rate of the universe would change, right? If there's a lot of mass in the universe, you'd expect there to be this slowing of the expansion rate because, you know, gravity's pulling in on all this mass and slowing the expansion down. But if there's not that much mass in the universe, relatively speaking, then perhaps this expansion rate would only slow gradually, or it would just continue on and never slow, just continue at its current rate. It used to be, right, up until the 70s and 80s, that this was the only possibilities. Right? These were the possible futures. And then astronomers discovered something really remarkable and very unexpected. By carefully looking at the expansion rate of the universe and how it's changed over time, and this is a result of better data that became available to astronomers, they were able to see that in the past, the expansion rate of the universe used to actually be slower than it currently is. And that what we've seen more recently is an acceleration of the expansion of the universe. And so that this more accurately portrays, as a rough sketch, how the size of our universe has changed over time. Now this was nowhere on the radar screen, that the universe is accelerating in its expansion. And the reason it was not on anyone's radar screen is because we don't know of any mechanism that could cause the expansion of the universe to speed up. And we have an intuitive sense that if there's an initial explosion of some kind, it might continue on, like the momentum of this explosion would keep it going. But to speed it up, there has to be some sort of energy that's being given to the universe as a whole. Astronomers really have no idea what this energy is and what is causing this acceleration. This was a huge discovery and really changed our picture of cosmology. And so what we see now is that our universe is actually an accelerating universe. And since astronomers don't know what's causing this, what form of energy, they give it the name dark energy. It's energy we can't see or experience in any other way other than when we see it manifest in the accelerating expansion of the universe. So now we have this crazy thing, right? We have this dark matter we've learned about before, this enormous amount of matter that's a part of galaxies that we cannot see and we don't know what it is. And now we have this dark energy, which is causing the acceleration of the universe as a whole, and we don't really know what that is either. To account for this kind of shape to the curve, right, we have to add a new cosmological parameter. It's sometimes called the cosmological constant. I think this is the symbol. You'll notice that this is not even in our textbook. Depending on which edition of the textbook you have, you won't even see the term dark energy appear anywhere in the textbook. Right? This is new-ish science, new astronomy. But this dark energy, this cosmological parameter is a measure of how much dark energy there is in the universe. So now these three cosmological parameters, Hubble's constant, omega matter, and the dark energy, these determine several things about our universe. How the expansion of our universe has changed over time, what the ultimate fate of our universe will be, and also the shape of our universe. Whether it's flat, whether it's curved in some fashion, those are all determined by these three cosmological parameters. Okay, so what I've shown you here is a somewhat simplified rendition of what this graph looks like. I want to show you what a little bit more sophisticated version of this graph looks like, and then also show you the real data that astronomers have taken and how that's helping us distinguish between these different possibilities. So here's a more precise version of the same graph, right, which shows you our current time right now, right? And how all four of these models are sort of consistent with each other at the current time. And then how that would be different if we go back or forward in billions of years. What's interesting here is it shows how the values of these two cosmological parameters allow us to determine whether we're in an accelerating, a coasting, this critical where it's just going to keep slowing down, or in a sort of a recollapse mode. It's particularly interesting. So these numbers, let's just take a quick look and see if we can pay attention to these, right? So in all cases that are not accelerating, this cosmological constant, right, would be 0. So if we have a cosmological constant, there's some form of acceleration taking place. The amount of mass in the universe is what's impacting here, whether we're coasting, whether we're at this critical, gradually increasing, or whether we recollapse, right? And that kind of makes sense based on this whole idea of mutual gravitation. What the current observations are telling us is that this top case is most consistent with our observations, right? That we have an omega mass here of 0.3, which includes dark matter and regular matter, and that this cosmological constant is approximately 0.7. So let me just show you what that graph looks like with the real data on it. So here you can see it's the same graph, right? It's just measured in slightly different units. So here's like the size of the universe on the vertical axis and time on the horizontal axis. And you see these cases again that we see here. And on top of that is data from a variety of different types of measurements, right? What we see from this data is that so far the results are certainly inconsistent with a recollapsing universe, which was in some ways sort of favored at a particular time in the 70s and 80s. While it may still be consistent with sort of a coasting case, just by the look, our looking at it here, you can see that the overwhelming amount of data falls on this accelerating line, right? So this is an area of active research by astronomers. There still is not a clear understanding by any means of what this dark energy that's causing this acceleration actually is. But we are beginning to tease out that the universe is clearly accelerating, and that we can sort of rule out these other possible futures and paths to our universe. So these cosmological parameters also play an important role in understanding the shape of our universe, and whether it's shaped positively, negatively, or flat. And so that's what you'll be reading about and learning about in the remainder of this lesson.